Video, I am going to discuss the solutions for the famous book of DigiQS solutions. So DigiQS is a textbook which is very standard for the interviews of the placement purpose and for internship purposes. So in this video, I am going to discuss the solutions of the first chapter of DigiQS. Let me introduce myself. My name is Jagannadh and I am an agricultural undergrad. So without wasting any of the time, so this is the first chapter of this book, DigiQS. So this is the first chapter, and I'm going to discuss each and every solutions for each and every question. So let's come into the first question. They're asking what is a bit. So sorry for bit is nothing but is 0 or 1. So bit is a binary. It's a binary digit. It's a logic 0 and it's a logic 1. So what is a nibble? It's just 4 bits. What is a byte? It's just 8 bits. What is a word? It's 16 bits. So 1 is to 4 is to 8 is to 16. 1 means the length of the bit, binary bit digit, whether it is 0 or 1. And 4 is the size, 8 is the size, 16 is the size. This is bit, this is nibble, this is byte, this is a word. Word in context of the digital electronics and not in the context of the standard English. So that is the first question. Coming to the second question, what is the weighted code? So a weighted code means, for example, if there is 1, 2, 3, 4. So if this is in a decimal, right? So this is there is something called as a place value. So for the place value of this is just it's 1. The place value of the second bit is 10. The place value is 100. The place value is 1000. Like the place value means if you multiply a particular digit with that particular number and if you add the sum, then that will be the resultant number. Like 4 into 1 plus 3 into 10 plus 2 into 100 plus 1 into 1000 gives rise to 3, 4. So in this way, a place value giving fixed value for each position such that upon multiplying that particular the digit from 0 to 9, that particular digit with that particular number, and after adding all those sums, all those products, will be getting the resultant number. So in this case, this is a decimal system, so the place value of each and every number will be increased by the raise of 10 in a GB manner. So this is what is called as a weighted code. And if coming to the non-weighted code, if you know about anything about the gray code. So the gray code means for the change of the binary digits of 1 to 2, 0, 1 and 1, 0. So this is represented as 1 and this is represented as 2. So if you look into this one thing, if you look into this example, from the changing of the 1 to 2, the change of digits is 2, the count of the change of the digits is 2. This is the simple case, and for the very complex cases, if you in the case of 16 digits or 16 bits, or in case of 32 bits, this number will be very different. It's very high. So in order to decrease this particular kind of problem, something is inverted as a gray code such that for the 2 it is represented as like this, 1 is represented as like this. Thus the change in the gray code, every time the change in the bits from the previous and the fourth one is exactly equals to 1. So this is the principle for each and every code of a gray code. So in this thing, gray code, it doesn't have any kind of weight. Like if you represent this as 2, then the second one is having the place value of 2, like 1, 2, 4, like that. If in the case of a binary system, in the case of a decimal system, it is a 10. But in the case of gray code, there is nothing like that. So that is an example of a non-weighted code. It doesn't have any kind of place values, unlike weighted codes. Like XS3 code is also there. XS3 code means for there is a number, you convert that number into simple binary number and add a 3 to it, that is XS3. That is some kind of encoding. It is used in some kind of encoding, that is XS3. Yeah, the next question is XS3. So what is the key feature of an XS3? The XS3 feature, if you take a 9's complement, like it's 1's complement, 2's complement, there is a 9's complement is there. 9's complement. So for the 9's complement, The excess code will be just replacing the zeros and the ones. If you do a simple example, then you will be getting to understand how it actually does. So it's just a simple thing. Knight's complement, like knight's complement is if there is a number 2, if it is represented in excess 3 code, then 2 plus 3 is equals to 5. So the binary representation of 5 is this one. If you replace this with ones and zeros, then what does it do? It will be 0, 1 and 0, right? So it is 2. So 5. So if you remove the 5 with the 9, then what we'll be getting is 5 with the 2. 9 minus 2 is equals to 7. It's a little bit complicated. Let's go this one. What is the ninth complement? Like self-complementing. Like the ninth complement of an excess 3 number can be obtained by simply replacing its ones with zeros and zeros with ones. So that is the thing. What are all the BCD numbers that can be numerically represented? Sorry, I missed this question. So in how many different ways a number 5 can be represented using 2, 4, 2, 1 weighted code? It's just weighted code. So if this is the weight, like in general it's 8 is to 4 is to 2 is to 1, right? So if this is the case, then we'll be having a fixed representation of the 5. Now it is a little bit tricky. It's not tricky, it's a little bit twisted. 2, 4, 2 and 1. So how 5 can be represented in this thing is 1, 0, 1, 1 and 0, 1, 0, 1. Like 4 and 1 and 2, 2, 1. Like there are 2 ways, right? 1, 0, 1, 1 and 0, 1, 0, 1. So these are the 2 ways in which you can represent 5 using 2, 4, 2, 1 weighted code. So the 6th question is, what are all the BCD numbers that can be uniquely represented in 2, 4, 2, 1 weighted codes? So in similar manner, BCD numbers, what are BCD numbers? It's 0 to 9. So 0 to 9 are called as BCD numbers, and what are all the BCD numbers that can be represented? Okay. Now what are all the bits that can be uniquely represented by weighted code? So using these, in general, like using 8 is to 4 is to 2 is to 1, we can represent each and every number, but now it is not the case. So what all we can represent is only 0, 1, 8, 9. Only these 4 numbers have a unique representation of this particular kind of 2, 4, 2, 1 thing. So that is the case. What is the condition for a weighted code to be self-complementary? So for a weighted code to be self-complementary, is the sum of the weights should be equals to 9. So that will be the self-complementary. For example, in the case of a 2, 4, 2, 1, 2, 4, 2, 1 code, if 2 plus 4 is 6, 6 plus 2 is equals to 8 plus 1 equals to 9. So 2, 4, 2, 1 code, if we add all the weights, then it will be resulting towards 9. So what is the condition for this weighted code to be self-complementary is that the sum of the weights of the particular code should be equals to 9. That's it. Convert the binary number into octal and hexadecimal. Like octal and hexadecimal. Octal means 8, hexadecimal means 16. Octal means 8, like that. So octal means 8, right? So 3. Hexadecimal means 4. We will be dividing this particular number into 3 parts. Like these 3 parts, then we will be getting 1, 2, 3, 4. These 4 divisions will be having, like for more clarity, we can write 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1 and 0, 1, 1, 1, 0, 1, 0, 1 and 0, 0, 0, 1. So in this way, like dividing the given binary number into few groups. In the 3 groups of 3 is an octal, and into groups of 4 is a hexadecimal. So that is the 9th question. Formulate a simple procedure for converting the base 10 numbers into the base 9 numbers. It's a simple. It's not that much simple. So basically, representing a base 3 number. We have xn minus 1, xn minus 2, and so on, x3, x2, x1, x0, and corresponding to the decimal equivalent given by p to the power of n minus 1 into xn minus 1 plus 3 to the power of n minus 2 into xn minus 2. Like it's like decimal equivalent, and so on. We'll be having 3 to square x2 plus 3 power x1 plus 3 to the power 0 x0. It's like representing this is a 3 number, right? If it is a decimal number, what will be in the place of a 3? In the place of a 3, it will be 10. That's it. So it is a base 3 number. So upon expanding this, we will be getting this one. So what we'll be doing is we will be merging these two ones. 3 to the power of n minus 1. We will be merging 3 to the power of n minus 2. It's like we will be taking 9. So 9 into n minus 2 divided by 2, 3xn minus 1 plus xn minus 2, like n minus 2 divided by 2, like square. This plus 2, right? This plus this. A plus a is equals to 2a, or a to the power of 2 is equals to 2a square, or a by 2 plus a by 2 is equals to a to the power of 1 by 2. So if 3 is there, 3 to the power of n minus 2 is there. For 9, what we should get? 3 square is there and 2 is not there, so into 2 by 2. That's what we did. 9 to the power of n minus 2 by 2 into 3 to the power of x minus 2 or plus of 3 into x of n minus 2 plus up to so on 3 to the power of 1 into x1 plus 3 to the power of 0 x0. Sorry, 9 to the power of 0. Sorry, excuse me. 1 second. So that is, so basically what we will be doing is we will be converting. If there is a number, then we will be converting it to decimal number. Then 3 into this number plus this particular number a, b, c, d, e, f, g, h. If this is the decimal equivalent of a 3 base number, like after decimal equivalent. Now 3 base groups of 2, groups of 2, groups of 2. 3a plus b, 3c plus d, 3 plus f, 3g plus h. In this way, we will be having this particular thing. So this is the resultant. If for example, if we do some example, then we'll be getting understood. I think there is also an example to convert that thing. So that is the 11th one. Formulate. Yeah, this is the formulate and removing that thing. But now we're doing this. What we should be doing to base 9. I think it is already converted to base 3. It is already in the decimal equivalent, right? Because it's 2. So groups of 2. Yeah, this one, this two, this two, this two, this two. This is a single thing. It's a single, like so 0 into 3 plus 2, 3 into 1 plus 1, 3 into 1 plus 0, 3 into 1 plus 2, 3 into 2 plus 2, 3 into 2 plus 1, 3 into 1 plus 1, 3 into 2 plus 2. If you do that thing, then you will be getting some pairs, right? You will get pairs like 2, 4, 3, 5, 8, 7, 4, 8. So in this manner you will get the pairs for these numbers. So these are the pairs, so these are the output resultant values. Now yeah, this is what conversion into the 9. Yeah, that's it, base 9. Based on conversion of a number, it's simple. 3 into number x plus 1, that particular y. Now, yeah, a number n has an n digits and the r ready. Let me clear this basic thing. So, yeah, this is done. This is done. This is done. A number n has n digits and r radix number system. What is r minus 1's complement and r's complement? Row. This what exactly means a complement? What exactly means a complement? So if complement means if there is a 9's complement, then what we'll be doing? We'll be subtracting the number from the 9. In that way, for example, if it have n digits, then it has an r radix system. So r to the power of n minus 1. This is the max number. This is the max thing. Like if 2 is there, so we have some 4 bits as there, and we have the radix 2. Then what is the max number? It's 15, right? For the 4 bits. For the 4 bits or for a number, the 615 is the max count we can achieve using only 4 bits in binary system. So that is what to the power of n minus 1 corresponds to. And so this is the max number. We will be subtracting the current value with the max number. That is the r minus 1 complement. That will be the complement. What is its complement? And r's complement. So that is the complement. This is r's complement. R to the power of minus n. And this is the total number. Sorry. I missed. Right. R's complement and r minus 1's complement. What is r minus 1's complement and r's complement? R minus 1's complement means r to the power of n minus 1 minus n. N is the number. And r's complement is r to the power of n minus the number. This is the max number. We will be subtracting the max number which is possible by using the n digits of an r radix, and this is the max number which is exactly plus 1 from previous thing. It is not possible using the one. It's r's complement. That is like for a radix 2, if what is the meaning of a 1's complement and what is the meaning of a 2's complement. So for the radix 2, for the 1's complement means the max number which is possible by the r number, the n small n number of digits is the 1's complement. And then what is the 2's complement? It's the max possible plus 1 and minus 1. Like actually we will be adding, after doing 1's complement we will be adding 1, right? So thus 1 will be basically adding plus 1 over here. So this is what we'll be doing for the r's complement. That is the case. The daily practical uses of the 1's complement and the 2's complement is the simple thing. The subtraction of the current number from the max possible number of using that digit is the 1's complement or r minus 1 complement, and r's complement is adding a plus 1 to it, or the max number plus 1, the highest possible number is minus the current number is called as r's complement. And 1 second. So next question, what is this? What is the 9's complement of BCD number 752? 9's complement, it's the radix is 9, BCD number it's 3, right? 3 and a BCD number, it goes from the 0 to n. So what is the max possible value for this 9's? Sorry, what is the max possible value? Here the 9, it's not 10, it's 9, means it's r minus 1's complement. So the max possible value by these three values, which can range from the 0 to 9, 0 to 9, 0 to 9, 3 BCD, that is 999. 999 is the max possible value by the three numbers, by three digits of BCD. BCD means 0 to 9. So this is the max possible, and it's asking 9 again. This is the, it's r minus, it's what? It's r minus 1's complement. It's 0 to 2 means 0 and 1, right? So like the total, the count is r. The count is the r. 0 and 2, 0 and 1 is the possible digits in the two base index. For the decimal or for the 10 based index, it's 0 to 10, and for the 9's index, it's BCD 0 to 9 only. For 10 means the count 0 to 9. For the 0 to 10 means it's 11. That way, so r is 10 over here. R minus 1's complement is the 9's complement. That is the max possible number which is possible using only the three digits. So from 0 to 9, 0 to 9, 0 to 9, what is it? 999. So 999 minus the current value is called as the answer for this question. Minus 752, it's called 247. 247, so that is the value of this one. Convert the gray code number from 11001. Let me remove this entire. Sorry. Cut. So the question, this is completed, this is completed, this is, no, this is not completed, right? Yeah. So 11001, this is the number. We should convert this to the binary number. What do we do now? So this is the gray code. It's simple. Gray code combination is, the first number remains the same, 1. Now what we do is, this is gray, 50 shades of gray, not, it's gray, and it's binary. This one remains the same. MSB, maximum possible digit, maximum sign digit, and your sign digit. MSB is the same, 1 becomes 1. Now what do we do now? We do XOR, XOR, XOR of this one and this one. We got the output 0. We got XOR of this one and this one. The second one, the output is 0. XOR, and we got XOR of this one and this one. The output is 0 again. We got XOR of this one and this one. We got the output 1 here in the last case. XOR, XOR. So 10001, 10000. Excuse me. That is the 15th question. 10001. Excuse me. Represent 45 the number system, binary, BCD, accessory, gray code. Why do we need to do this? 45 is there. Just we need to know how to convert a particular number into the binary. So 45. If you look into 32 is 510000, right? 1 2 3 4. This, if this is 1 1 1 1 and it's 15, and if it is 1 and it's 16, so it's 32, right? Okay, now what's 45 here? So it's 32 and 45, 110. Excuse me. So this is what, which is remaining. 1100 means it's 10 and it's 12 basically. So sorry, it's 13. Yeah, it's 13. 32 plus 13 is equals to 45, right? So 13 is represented as like this. So this is, we will be repeating like this. Adding this one to this one, we got 1 0 1 1 0 1. This is the binary representation of 45. And to get BCD, we just need to add represent each digit separately in binary. Excuse me. Man, so I think I missed. Yeah, it's fine. Excuse me. So in BCD we get 0 1 0 0 0 1 0 1. This is what we get in the BCD. And for an access 3, we need to add another 3 for it, means 1 1 to it. It becomes 0 0 1 0 0 1 1 0 0. For an access 3, it's 0 1 1 1 1 0 0. To see to each digit. For this one also 1 1 we will be adding. Now gray code binary we used to do the same procedure. Like binary we should do 1 with XOR, 1 with XOR. We will be doing the same thing, 1 and 1. Like, yeah, here there is a space. So value is 0 0 1 1 0 1. 1 will remains the same. Yeah, it's remain the same. Now the resultant value, what the XOR of these two values is 1. The XOR of these two values is, sorry, I think yeah, XOR of these two values is 1. XOR of these two values is 1. XOR of these two values is 0. The XOR of these two values is 1. XOR of these two values is 1. That's it. So it's basically 1 1 1 0 1 1. That is the answer. The gray code. Gray code, exams 3, BCD, binary. Give the range of numbers that can be represented using AND bits in the 2's complement method. 2's complement method. 2's complement means we'll be subtracting the max number with the minimum, right? So if we subtract the max number, then what from the zeros possible, like if you reverse each and everything, we'll be getting the range as minus half 2 to the power of n minus 1 2 plus 2 to the power of n minus 1 minus 1. This is what we'll get the range, because 2 to the power of n minus 1 means it's alright, and it is not possible because the first bit is, we will be using this first bit for other purposes in the 2's complement, so that's why it's not there. Coming to the 18th question, what is the minimum number of bits required to represent the number in the range of minus 5 to 23 using 2's complement method? Bro, the same math. We will be equating this, so we will be equating this to the minus 5, and we got some number, and is greater than or equals to 6. So the minimum number is 6. What will be the resultant of all the zeros are returned from the LSB side until 1 is, it's 2's complement. Yeah, it's 2's complement, right? 2's complement. This is what the definition is. For the particular design, which uses 5 bits for integral part and 7 bits for the fractional part. The resultant of some operation is 7 8. I think there is some. I've done this question, but the answer is not tallying with mine one, so I think there is some error in this question. So let's leave this question. I think some error is there in this question. Convert 0.95 to its binary equivalent. Bro, it's not quite lengthy process. I will be yeah, this is the process. So like 0.95 into 2 into 1.90, like this is the given number. The number will be continuously multiplying by 2. So 0.95 into 2 will be getting 1.90, and now this is multiplied by 2, we get 1.90. This is multiplied by 2, we got some number 1.60. Like in this here, the fraction doesn't stop. Uncountably it will be repeating the same again and again and again. So like if you look into 110 and again we got to 1.16, so here it doesn't matter what the value over here, it again repeats the same. So it is better to so this is what officially will be doing. So in the representation of this, because it doesn't completely become a 2 at somewhere, or it becomes 1 or somewhere, or it becomes 0, it goes on increasing. So this the value is also goes on increasing. So it's 0.11, and the pattern here is 1100. It's this easy pattern, so it can sometimes it can be very difficult, like 7 to 8 bit length of the pattern. We should continuously multiply until we get the same again. So here if there is a decimal given, then it is sure that whether it will be some pattern which is continuously repeating again and again and again, or that will be becoming a single integer such that it stops over that point, so that we can make an end point over here. For suppose 0.125 into 8, like into 2 into 2 into 2, we will be getting like here how, yeah, I actually forgot to say how you get this one. Once here we will be taking the fractional part into twice, and if we got over 1 over here, like if the value increased to 1, it is greater than 0.999, it's greater than 1, or it's equals to greater than or equals to 1, then it's the value is 1 for that particular integer. Sorry, it's a fractional part, right? So if you increase that value again, if you multiply 0 point, you will be breaking that fractional part into 0.1.90, kick out the 1, you got the 9.90, and 0.90 multiplied by 2, you got 1.80, you got x greater than 1, so we got 1 over there, and you kick out 1 again, you multiply 0.80 into twice, you got 1.60. You can kick out 1 over there and you got 0.60. Multiplied by 2, you got 1.20. Kick out 1, you got 0.20. 0.20 multiplied by 2, you got 0.40. Now it's not greater than 1, it's less than 1. So it's the 0. So in this manner you should make 0, 1, 0, 1, 1 is the particular, for that particular multiplication, what is the value? It's whether it is 0 and whether it is 1. For 0.125 case, if you multiply it by into 2, is 0.250, so it's a 0. If you multiply it by again 2, it becomes 0.5, again is 0. If you multiply it into 2, it becomes 1, so it's 0.001. Sorry, 0.001. Yeah, that's it. We will be multiplying 0.125 into twice, and to again twice, and again by 1. So that's how we will be doing on this. Sorry for showing you the hints. This is a normal thing you make. You can A, B, what is A, what is B, 1010 is A. Sorry, 1001 is, yeah, 1010 is A, 1011 is B, 1100 is C, A, B, C, D, E, F till you got the like 15, 15, 10, 11, 12, 13, 14, 15, A, B, C, D, E, F. So this you will be converting these values to these values, and you just do the simple subtraction, and that is the resultant value, because here the base is same, bro. Yeah, so 171 and 62 they have converted into the normal value. It is 109, and you got, it's normal. You just need to convert this value into normal decimal value. You do the simple math. It's minus, or whether it is a positive, whether it is a multiplication, whether it is a division. You do the math. If it got functional fraction again, you go, you know the procedure which we have done in the previous question, right? So we'll be repeating the same procedure again. For the fractional part alone, it's remember, it's we'll be making that binary representation of fractional part in the consecutive manner, like the way we got in, we multiplied by 2, the way we got if before that, like if it is the in the left hand side of the decimal point, then we'll be doing in the reverse manner, like the way we got started earlier by dividing the greatest number, or by 2 we will be getting the some zeros and 1 depending upon the divisibility of the particular number by 2, and at the end we reverse that whole number. So this is not the case for the decimal part, which is the right hand side of a decimal point. So that is the case of 22, and that is 21 is over. Solve for x, the same, like can't make everything to decimal, do the simple math and do the things. Yeah, this is nothing explanation. It's not explain the detailed process of BCD addition. Bro, what is BCD addition? It's not but simple. Perform BCD additions of this thing. So I will show you. This one. What is this? Like 101010110. Same, if like it's simple, 190, it's 1011111. That is, now what is this? 1111. It is a 4-bit number. This is what a simple thing. It's like if it's 4-bit number, it's greater than 9, and BCD is only represented in till it's an overflow. So BCD is represented only normal thing. So we will be adding 6 over there, like 0110. Further, this is a standard procedure. Like here, we need to add 6 to the number if it becomes an overflow. BCD is, remember BCD, wherever the BCD is given, then that BCD is only represented in, you go 0 to 9. Only 10 numbers are allowed. 0 to 9 is only the BCD. If wherever it becomes BCD, you should check which is the index, or which is the system, whether we are using a BCD, whether we are using a hexagonal, before doing an operation, and after doing the operation, whether it is a multiplication or whether it is a subtraction, whether it is an addition, after that operation, if that is again the same, if it is in the limits of the particular decimal or particular system, then there is no overflow. If it is less than the negative possible value for that represented in that limited values, then that is an overflow. And if it is greater than the max limit, then it is again an overflow. Then you should do some small additions like this. Now we are adding a 6 over here. So 10101 is the thing. That is the thing. That's the I think I have completed. That is the last question, I think, right? Yeah. So that is the last question of 26 questions. So with the 26 questions, we have completed the chapter 1. If you have any doubts in any of the questions, please feel to explain. And my voice is a little bit harsh, and I have taken a little bit breaks in between. And I think I have confused for the 2 to 3 questions in between also. Sorry for those all things. And Please supporting with the like, share, subscribe, and it's the first video of this series, and you can expect a much more clear explanation with much more good handwriting of mine and good voice of mine. Sorry for this, I can't do this thing unless you support me. So here's what for today. Signing off. Yeah, thank you guys.